All right, good morning and welcome to Business Analytics and Data Science. It has been a while. Great to see you again. I'm sure you had a fantastic course last week with Alisa, and unfortunately today it's going to be me again with the second part on our current chapter, Ensemble learning. So we are already approaching the very cutting edge type of stuff, discussing those machine learning techniques that are yet in the process of finding their way into industry. By far, it is not the case that every organization would have adopted these type of algorithms that we've been discussing last week and will continue to discuss today. Many organizations, including innovative organizations, including startup type of organizations, are in the process of evaluating these things, these methods, thinking about adoption, but are not there yet. With regard to today, we have, I am afraid, a quite rich agenda. As usual, the main topic today is the boosting algorithm, which is yet another ensemble algorithm. An ensemble algorithm, however, that adopts a different approach compared to bagging and random forest, roughly speaking. If you know about random forest and recent versions of boosting, you know what you need to know, really. These are the key challenges that you may want to consider when predictive accuracy matters, may want to consider as an alternative to logistic regression. And with only these three algorithms, logit, random forest, and boosting, you really have access to a very powerful set of tools. There are many, many others, but I believe these three are the most important ones, definitely as long as we speak about structured data. When we enter the space of textual data, image data, non-structured data, different story. But for structured data, the type of problems we've been examining in the past weeks, these three are the most relevant set of learning algorithms for prediction, or the most relevant set of supervised learning algorithms. So boosting is the core today, and we'll spend some time, and possibly, perhaps, we will then also have time to look into heterogeneous ensemble methods. I would like to introduce one such method called the stacking algorithm. Well, we'll just see whether we get there. This is mainly a research type of technique, or a technique that you want to know about if you consider participating at Kaggle challenges. These challenges where everything is about predictive accuracy and nothing else matters. Then stacking might give you a little edge in terms of accuracy, but when we talk about production environments and are concerned with really deploying models in the real world, you would not use a stacking technique. Quick reminder, ensemble models. I was undecided whether to use method or model. This is why medals came out. So ensemble models are our technique of choice today. You recall this picture. Boosting is yet another ensemble, so we are still in this picture. We develop many base models, all of which solve the same task and combine them. That's as far as the introduction goes. What is different from last week? The original algorithm is due to Robert Shapiro and Jörg Freund. These were computational computer scientists, you might call them. The time boosting came out was pretty much the same time when Bryman published his bagging paper. So the idea of combining multiple tree models was already sort of around, let's say. And Freud and Shapiro, they started from the observation that if you face a complicated problem, a complicated classification problem, say, with a fairly complicated decision boundary, high degree of nonlinearity, etc., solving this problem with a single model might be complicated, or finding the powerful model that takes care of all the complexities in the data might be a very hard task, whereas it might be a much simpler task to come up with a rough, maybe even weak model that only does a little better than random. The example they used was that of a spam classifier. If you want to build a system that detects spam in email, that can be fairly complicated. Judging by the amount of spam I receive every day, I would agree it's obviously a fairly complicated task, which must be the reason why nobody has yet developed a fully satisfactory solution. At least not for me, at least. I'm not sure what your opinion is on that, but we can imagine that detecting spam is fairly complicated. Also because spammers routinely update their approach to trick spam detection systems. So it's complicated. And yet, if you think about the type of spam mail that you consider, there are certain cues, triggers, let's say, that signal spam. So anything about win, or a monetary value in the regions of billions. You know these mails, right? You want 300 billions, just give us your email. No, not 300 billions. Normally spammers are a bit more modest. Or Prince Mutubu from whatever need to collect his heritage. You know these type of spam emails, right? There are certain cues. Anytime you have won something, or also invoice, you get many emails where you are accused to have not paid an invoice, and where you are threatened that this invoice, this due amount, will now be sold off to some collection agency, which will then nag you. There are these cues. Invoice is one of these cues. Many spammers use this type of setting where they come up with an invoice and pretend you have not paid this invoice. So the term invoice in an email might be somewhat indicative of spam. Somewhat. You get many regular invoices by email, of course. So a simple classifier, if email contains invoice, then spam, would certainly not do its job. But giving this pattern that spammers might send you a fake invoice or claim you have failed to pay some invoice might result in this naive rule: when email contains invoice, then spam, it might actually do a little better than random guessing. And what Shapiro and Freud argued is that these very naive, simple rules are easy to develop. You can think of many such cues. If email contains winning, then spam. If email contains lottery, then spam. It's easy to come up with these very weak learners, and maybe there is a clever way to combine them to ultimately obtain a powerful learner. That was sort of the starting point. It also coined the terminology of weak learner. In a boosting context, you often call the base models that you combine weak learners, and very often these in fact are fairly simple models. For example, last week you learned how in random forest it is common practice to combine deep decision trees. Breiman himself even recommended to combine fully grown decision trees at the maximum depth possible, using your data or considering your data. And in boosting, often we use decision trees with 2, maybe 3 levels, or maybe even stumps with only 1 split. This is where the term weak learner came from. And the idea again was that it might be easy to create a weak learner, and it might be easy to create many weak learners, and maybe we can combine these many weak learners into a powerful model. That's the overall paradigm, if you wish. And now the key thing in any boosting algorithm is that the weak learners are not combined in an independent manner, as they are in random forest and bagging. You just build a bunch of trees and then you put them together. Boosting does not work like that. Boosting builds one model at a time, one weak model. Because it's a weak model, it will make errors. Boosting then examines these errors and tries to build the second model in such a way that it remedies the errors of the first one. And then you put model 1 and 2 together, you have an ensemble. Boosting would then examine the errors of your current ensemble and trying to add a third model which remedies those errors. So it's a way of continuously trying to improve upon the error, to improve the error in a more direct way than bagging, for example, where you just count on the bias-variance trade-off and hope that by combining many models you reduce the variance, and if these are complicated enough, have low bias, you achieve a nice balance in the bias-variance trade-off. Boosting tries to minimize error more explicitly, more aggressively, if you wish. You build your next model exactly in a way that is geared to reduce those errors that you currently make. Statisticians refer to this paradigm as additive modeling, sometimes. More on that later. Let's try to picture that. Here's an example of a possible data distribution. We face a classification problem in 2 dimensions. And now we imagine one weak model, which might look like this. A simple split, a tree with only one level, or a decision stump, as they are called. We do note how our trees make certain errors, and in fact we can count these. Let me introduce some notation. Don't worry about beta for now. Eventually this will be a weight of this first simple weak classifier. Only note the error, which I denote by epsilon. It's 0.3. We have 10 data points, and our first weak classifier misclassifies 3 points. The 3 red points are misclassified, so we have an error of 3/10, which tells us something about how well this classifier does its job. What boosting now does, it would increase the weight of these misclassified data points, and I'm trying to depict that by making the points a bit fatter. And the other data points, where our first classifier already got them right, we decrease their weight. So note how they are now a bit thinner than before. Now we continue. We fit a next classifier to this data, where the data points now carry a weight. And the weight means that if I misclassify the points with a large weight, I will be penalized more harshly in a way. Or put differently, these weights give our classifier an incentive to get the high weight points right. So the next classifier might look like this. Noting that these 3 red squares carry the strong weight, it would avoid misclassifying them and might create a decision boundary as shown in this picture. So now we would again misclassify 3 data points, 3 green data points this time. But because of the weights, let's say our classification error will not be 0.3 as before, it will be something else. And I just guessed this number, 0.21. So what you may want to note down is that the reason why the error for classifier 2 is now 21% as opposed to 30% is because the 3 misclassified points carry a lower weight. And I mean, somewhat that does make sense. We already have one classifier that gets the small points right, that classifies these correctly. Hence, we can downweight them. We can tolerate these 3 errors to some degree. It's not the error of our ensemble. These points, it's only classifier 2 which gets them wrong. But we can tolerate that because we also have classifier 1 that got them right, these 3 points. So it does make sense that classifier 2 focuses specifically on the 3 big points here, because these are the ones that our first classifier was not able to classify correctly. Or more generally, these points will be located in areas of our attribute space where our first classifier is not so good. So we want to focus our attention on these issues. Now we use this new error to update our weights again. And the situation in the third iteration is such that we have the 3 red data points in the upper part, which classifier 1 got wrong and classifier 2 got right. And we have the 3 green data points that classifier 2 got wrong, but 1 got right. So here they are misclassified once and correctly classified the other time. And the other 4 points, by now, they have been correctly classified twice. So we can get some intuition that these 4 data points, they appear in areas of our space where the classification is fairly simple. The obvious cases, if you wish, where getting the class right is easy. So we further decrease their weight, and now they become really tiny. And the remaining 6 data points, which have been misclassified once each, they have somewhat equal weights now. Given this, our third classifier might identify this decision boundary. After all, it gets the important point right. It does make some errors though. 3 errors, again, 1 green and 2 red errors. And now I just put a statistic of epsilon 3, the error of the third classifier equal to 14%. Again, we make 3 errors, but I say, or I claim the error rate is only 14% because I consider the weight of the data point when calculating my error rate. And maybe this is 14% here. It depends on the weights, but for you it's only important to note the tendency. If I get small points wrong, there is an error, but the error is not so substantial. And eventually we put these 3 classifiers together. And here I also incorporated the values for beta, which I have not discussed by now. I just made them up. These 42%, 65%, and 92% that you see here, they represent the classifier weights. We'll see soon how they are calculated. They sort of pop out of the boosting algorithm. And if we combine these classifiers, put them together and weight their forecasts, hopefully we get an ensemble classifier that gets all the points right, as shown in the lower picture. This is sort of stylized, right? It's not that you take only the correct part of the boundary from classifier 1 and pool that with the correct part of the boundary from classifier 2. It does not work like that. We use the predictions for all the data points and then weight these. But the picture is meant to show what we would hope to obtain. And a final note on these classifier weights, these beta weights, you may note that the third classifier, well, it got the largest weight and the second largest weight I gave to classifier 2, and the smallest weight I attached to classifier 1. This also was on purpose. There is some sense to that. Classifier 3 was the most accurate one. The error for classifier 3 was the least. And the error for classifier 1 was the largest. If you go back to the slides, you'll see this tendency. And it does make sense that we put the largest weight on our best classifier, the one with the smallest error. And the next thing is we need to formalize that somehow, to have an algorithm that we can program. Let's try and do that. As usual, we start from our training data, pairs of x and y, x being a vector of attribute values and y being our target. Let's say it's binary. And then we need a priori to decide upon the number of steps, which is equivalent to our ensemble size. I put a capital T here. It's the overall number of weak classifiers that you will combine. You need to set that a priori. It's not determined automatically for you. And then for each classifier, we first construct our data set with the weights, construct data distribution D of T over all the n examples in our data set. And to do so, we use the error from the previous iteration, epsilon t minus 1. Previous iteration, t minus 1. I didn't bother with elaborating on how we do that, just note this is what we do. Then we fit our weak classifier to this data, dt, which comes with weights. And then we determine its error. And this error is what we need to calculate the classifier weight, beta t. Beta t is a function of the error. And the data distribution in the next iteration also will be a function of this error. And we continue this exercise for capital T rounds, obtain capital T classifiers, weak classifiers, and a weight for each of these classifiers using this recipe. And then we can just average the predictions of all these classifiers, weight the average using beta, and there is our boosting ensemble. So this is a step where we need to dig deeper and agree on a way how we can do this, how we organize the weighting, and same here. How we set the weight as a function of the error is something where we need to determine in order to have a programmable algorithm. Just in case you worry, this is just a way to write down that we want to find the error of our current classifier T, which I denote by the probability that classifier T outputs the true label, or well, does not output the true label. And here is a more formal recipe which explicates these 2 points, how the data point weights are calculated and how the classifier weights are calculated. And it's in fact the recipe that Freud and Shapiro recommended in their seminal paper on the adaptive boosting algorithm, or AdaBoost for brief. They first of all initialize the weights of the data points just by 1 over n. So every data point has the same weight in the first iteration, which intuitively does make sense, right? We have not classified any data point correctly or incorrectly, so in the first iteration every point has equal weight, which we just set as 1 over n, the number of data points. So if you have 100 points, every point carries the weight 1 over 100. Here we see how Freud and Shapiro calculate something like the weighted classification error. It's not super fancy really. You can convince yourself that with the initial weights wi 1 over n, this formula just counts the total number of points you misclassify and gives you the vanilla classification error. with wi, however, deviating from 1 over n, varying across data points, the error measure that you obtain will be somewhat weighted. More interestingly is then maybe, okay, that was a weighting. More interestingly, I don't need to write that, I have my animations. The weight update. Here we see how we update beta, weight of the base classifier, as a function of the error, using some logarithmic function. And lastly, here we see how Freud-Shapiro recommend updating the weights of the data points, the wi. And well, these formulas appear. We can look at their shape to determine that they make sense. This approach has some theoretical properties which were uncovered only after Freud and Shapiro published that. So although I don't know, but maybe this was just engineered by trial and error using these weighting functions. The theory around boosting was published only later, and not only by Freud and Shapiro, but also several others. So I would assume, but this is speculation, that the theoretical underpinnings were not fully understood by the time this was published. So maybe Freud and Shapiro themselves, maybe, just speculation, maybe also just use such an exercise where they would examine these functions. Here we see the functional shape of the beta with respect to the error, which, I mean, yeah, how to interpret that? We have the classification error on the abscissa. We think about binary problems, so it's either good or bad, yes or no, right or wrong, 1 or 0. A coin flip would achieve an error of 0.5. And a weak classifier should be slightly better. So maybe the flat area that we note in the realms of the error being between, let's say, 0.3 to 0.7 maybe, fairly flat this functional, right? Maybe this is because we assume that a weak classifier will achieve an error somewhere there. And if it does not, if it's very good, error being very low, close to 0, or very bad, then our weights really make a big jump, right? This is a way to describe this functional shape. This part here says that if a classifier is very poor, it gets a very large weight, negative weight, but the absolute in magnitude is very large. Does that make sense? We really consider class labels here, so we really count errors, and a classification error of 100% then means that you get every label wrong. So just by inverting your classifier, you get every label right, and it's perfect. So this makes sense. Here is then the functional shape of beta exponentiated, and this exponential is used when we set the weights of our data points. And well, again, we can try to reason a little bit what this means. You see how the weight update depends on whether a point was classified correctly or incorrectly. These are the correctly classified points. H of t of x is equal to yi. That's just a formal way to say the point was classified correctly. So we would want to decrease its weight because our classifier just got it right. So we take the last weight wi and multiply that with e to the power of minus beta. Let's again try to make some sense. We note from the previous chart how beta could be anything from minus infinity to plus infinity. You can sort of insert these values or play a little bit around with this function and then convince yourself how, well, the change of the weight is the more extreme, the larger the absolute value of beta, which does make sense if it's very strong classifier, if you have a very strong classifier and it classifies a point correctly, if you think about it, it's nice that it classified this point correctly, but it was a very strong classifier. If it was a rather weak classifier, but coincidentally, one point it got correctly, this has a different meaning. And in a nutshell, these weights are meant to capture these different notions of how one thing that matters is whether a point was classified correctly or incorrectly, but it also matters whether it was classified correctly or incorrectly from a strong or a very poor classifier. Well, again, there is some theory underneath boosting, but I won't touch upon it in the scope of ADA boost. And also empirically, you can show, or it has been shown, that this type of recipe to construct a boosting ensemble works fairly well. And the final ensemble then just is the combined output of all the base models weighted by beta. Quick excursus into theory, boosting in the scope of the bias-variance trade-off. We are putting more and more weight on the difficult cases. You can imagine that eventually you will get these difficult cases right. At some point, their weight will be so extremely large that any new classifier that you add will be geared exclusively towards the difficult point. Long story short, eventually you can drive your error on the training sample down to 0, which is shown here by the green line. It oscillates a little bit, but here you have t, and here we have error. Sorry, you need this information to read the chart. So on the training sample, if we add more and more members to our ensemble, eventually we drive the error down to 0. And this makes sense because every new member that we add is geared towards the current errors. This bears the risk of overfitting. So what is often done is, in order to find a good number setting for t, the size of your ensemble, you check the error on an independent holdout dataset, a validation sample, which I've shown in blue here. The blue line depicts the error on an independent dataset that boosting doesn't see. And it's real-world data, so we observe this nasty pattern that our blue line does not really exhibit a clear minimum. We have these points here, but these are just bumps. So not sure whether you would want to set t equal to these values, or maybe rather go for that value, arguing that we are here at a point where the downward trend in the error on the validation sample decreased. Generally, this is a meta parameter that might need some tuning, and drawing on a study by Domingos in 2000, which then came out like 4 years after the ADA boost algorithm was published. He was sort of showing that by combining these base models, you reduce the variance, so that is good, but as far as the ensemble overall is concerned, although every tree is weak, by combining these many weak learners, you also reduce the bias. So unlike bagging, which works only by bringing down the variance, prevailing view is that boosting reduces both bias and variance, which is maybe enough. The question is, what actually is the output of our small h, of our classifier? Does it predict a class membership probability, or does it give us a class label? And if that is a class membership probability, we need to normalize that so that the combined forecast also is a probability. We can't just add them up. If we interpret the output of our boosting ensemble just as a score where large values indicate high tendency to be of one class and small values indicate high tendency to be of the other class, but we do not interpret it as a probability, we don't have to normalize that. So dividing by capital T is probably a good idea to normalize your forecast and put it on the same magnitude as whatever comes from the weak classifiers. But in terms of scoring data points according to how likely it is that they belong to one class or the other, it does not really matter. If you sum up these outputs and weight by beta and divide by capital T, it might well be that you are not between 0 and 1. Typically you will be actually, but it's not certainly guaranteed that you have a probabilistic output. So in fact you need some more elaborate way of normalizing that if you want boosting to give you a probability. But very often, we talked about the AUC, for example, on receiver operating characteristics. Very often, what you really want to achieve is rank ordering your data points. For many problems, this is what you need. You rank order your data points, and then you set a threshold and say everything above is class 1 and below is the other class. Decisions are binary. You make credit decisions, you either accept or reject applications. Decisions are binary. So you need a rank ordering of the cases according to their risk, and then you, considering your business strategy, decide on the cutoff. That is the typical setting in many problems. The cutoff embodies cost-benefit considerations, and you set it, and your classifier, your learning algorithm, your model delivers you a ranking of the cases. And then the scale of this ranking does not matter very much. AdaBoost is rarely used these days. It was replaced by gradient boosting. But it builds upon these foundations. So this is why I still discuss AdaBoost first. Gradient boosting was developed by Friedman in a very, very seminal paper that he published in 2001, the gradient boosting machine, he called that. And essentially, Friedman was a statistician. He's with Stanford, and by that time, he already was with Stanford, I believe. He was also part of a bunch of authors who wrote the famous book on decision trees. He was really one of the major players in statistical learning at that time and still is. Essentially, his paper clarified some or build a bridge between what the machine learners did with their boosting stuff and what statisticians already have done before. And he sort of reinvented boosting as an additive model. He also extended boosting to non-classification problems like regression problem, but also problems in survival modeling, ranking problems, which was quite a major advancement at that time. And he made major contribution to the underlying theory of boosting. Okay, so here we see the formula without the normalization again. And he reformulated that as an additive model. And then he basically abandoned all this weight updating thing because he realized that you can do that in a smarter way. He still follows the very boosting principle. It's an additive model. You combine models in an additive manner, adding one model at a time, so as to correct the mistakes of the previous model. All that stays the same. That is boosting. It's always core to boosting. Just AdaBoost had a certain recipe how to do that, weighting data points. Which, by the way, works only if your weak classifier is able to process data point weights. Otherwise, how would you ensure that your weak learner is geared toward the difficult data points, the one with a high weight, if the base learning algorithm is unable to process weights? In fact, many algorithms are unable to process data point weights, which is maybe an issue with AdaBoost. Friedman realized how you can use gradient descent to develop your boosting ensemble, or more generally, to determine the parameters in a boosting ensemble or in an additive model. And if you think about the parameters, I mean, the parameters essentially are the betas here. Okay, to be fair, the base learners, the weak learners also have parameters. But he essentially re-implemented the paradigm, incrementally correcting the errors using gradient descent. And this is a smarter way compared to this weight updating, and shown to be a more effective way compared to this updating of data point weights. But now you need gradient computation, so the mathematics become maybe a little bit more elaborate. Essentially what we need is the gradient. In order to carry out gradient descent, we need an objective. And this objective we differentiate with regard to some parameters. So let's try to get our minds around this in machine learning. Our objective typically is some loss function or error measure. Also note this terminology. Machine learners talk a lot about error measures, and statisticians typically think in the space of loss functions. Same thing, just different name. So we have some loss function that captures how good or how poor our model is, our current model. And this loss function depends on certain parameters, and we need now the derivative with regard to these parameters. And in our case, we can think of these parameters as the betas, the weights of the weak models in our boosting ensemble. The good news is the gradient exists. The good news also is Friedman found them all for us in his 2001 paper, which is why he well deserved all the credit he got for that paper. And in terms of getting out these gradients, you see here a rank ordering. It's the easiest for regression problems, and this is why we will look at regression problems in the reminder. It's more complicated if you think about classification problems, and it's even more complicated when you think about ranking problems or survival problems. These are different modeling tasks. So although I used to talk a lot about classification, let's make a jump and consider a regression algorithm for now. So we try to predict some continuous target, maybe sales as a function of price and advertisement spending and competitor pricing, and whether there are running promotions or not, season, etc. So y by now is a number. We still have data points x and y, but y is a number, a real number. And as we are accustomed to work with the squared error loss function in regression, you know OLS by heart, you know squared error. Let's take that as our loss function. We measure the adequacy of a model by means of squared error. The lower the better. So let's say we start our boosting process with some initial guess of a weak model. We could just, y is a continuous variable. We could just calculate the average of y, the average sales, and use that as our initial forecast. We just forecast the average, as simple as can be. We ignore all the x, but we just need a starting point. So this is to say it's easier to come up with an initial model. Let's call it HO. It's an initial model, so it will not be perfect. There will be errors. Let's calculate the errors. So I just invented some numbers, right? So maybe our model predicts a quantity of 0.8, while the true quantity y1 was 0.9. And for another data point, maybe our initial model predicted a quantity 1.4, while maybe the actual quantity was 0.3, 1.3. It will make errors, right? And now we want to try to improve these errors upon these errors. We want to make the model better. But we still live in a boosting world, so we cannot change our model HO. That's forbidden. Boosting does not allow that. All we can do is we can add another model, H1. So maybe H1 is yet another regression tree we fit to our data. And then staying in this boosting paradigm, the next prediction or our updated prediction will be HO plus H1. Let's ignore about the weights for now. Ultimately, the prediction will be beta O times HO plus beta 1 times H1. But essentially, the next prediction will be the combination of HO and H1. We would like to the sum of these model predictions, HO plus H1, to be close to the true target, right? This is our game. After all, we're doing regression. And ideally, we have that for all the data points. That's sort of our goal. That is what we sort of like to see. That HO plus H1 is exactly equal to y for the first data point and the second data point and the third and fourth and so forth, all the way down to the nth data point. We could just rearrange our equation a little bit, because we need to answer the question, what actually is H1? What's the next model to be added? How would we like this model to be? And then if you turn around this equation, we obtain this very interesting part here. Well, I find it very interesting, because what's written there on the right-hand side, that's the actual y minus the forecast, HO. How do we call actual minus forecast? I mean, that's just the error. Or if you like, the residual. So how can we achieve that? How can we build a model that does that is equal to the error or is equal to the residual? Let me rephrase that. How can we build a model that predicts the residual? Why not just regressing on that? So we again update our data set for the next iteration, just that we don't introduce weights as in boosting. We manipulate the target variable, and our new target will just be the residual. And by carrying out this estimation, trying to build a model that predicts the residual, we would hope that by combining HO and H1, we'll get a better model. After all, we are training H1 to learn the error. Very explicitly now, we train it to predict the error. Okay. So yi minus HO of xi are the residuals. They are the parts that HO can't predict well. The role of our new model, our next member, is to compensate this deficiency of HO. We build our next member model H by regressing on the residual, and then if we find that the sum of both is still unsatisfactory, we just continue. We find the residual of HO plus H and build a next model, H2 let's say, by regressing on that residual. We can do that many times. Quick excursion. It's called gradient boosting. We haven't talked much about the weights, the betas. This is where gradient descent comes in. It's just an optimization routine, first order method, so we only consider the first derivative, right? We're trying to minimize some multivariate functional or generally some functional. And the algorithm basically proceeds by, in an iterative manner. We have a current solution, and we're trying to improve upon that by making steps, changing the solutions in a stepwise manner. And the way we change it depends on the gradient of the current point, which is the point, or the gradient gives us the direction in which the functional increases the most. And if we take a step in the opposite direction, this will be the direction in which the functional decreases the most. It's very easy to convince yourself how this makes sense in 2 dimensions with a univariate functional f of x, but it also makes sense in more dimensions, and typically you have these plots. This one I borrowed from Wikipedia, where you depict the contour. The circles depict the magnitude of my function, my multivariate function, which depends on x1 and x2. So you can imagine an x1 here and an x2 here. And then inner circles represent lower functional values. So this is the sweet spot. It's the unique combination of x1 and x2 that produces the smallest output of my functional. And starting from an initial guess, x, now, here, I'm trying to change my solution stepwise in order to move closer to the sweet spot. And I do that by following the directions of the gradient, making steps in the direction of a negative gradient. That is the standard learning rule in gradient descent. We have our current solution, are denoted by xn, and we make a step in the direction of the gradient, which is this triangle, is the nabla operator. So that's just my way of denoting the gradient here. The gradient of our loss function, we make a step in that direction, but in the direction of the negative gradient. This is why we have minus, and this parameter gamma is called the learning rate. It governs how large a step we make, whether it's a big step, whether we change our current solution a lot, if gamma is large, or if gamma is small, we change our current solution only a little bit, and thereby take a small step in the direction of a negative gradient. It turns out that residuals and gradients coincide if we consider a least square loss function. If least square is our loss function, then the residual is equivalent to the gradient. Hence, fitting a model to the error, fitting a model to the residual is equivalent to fitting the model to the negative gradient. This holds true only for squared error loss. For other type of problems like classification, where you have different type of loss functions, for classification you use typically a function, well, cross entropy, which is just the likelihood function if you wish. The derivative and the residual, well, they don't coincide anymore, but you still are able to apply this logic. You just make steps in the direction of the negative of the gradient, and this will guarantee that you reduce your error, that you change your solution such that your loss decreases. And that's the whole point. So you minimize your loss using gradient descent. And for a regression problem with a squared error loss function, I put the formulas here. So the loss function you see in the upper part, ignore the 1/2, it's just a scaling factor for convenience. The loss function is y minus h of x, our model. H of x is our model, y is our actual. We find the residual, we square that. If we find the derivative of this loss function, from here to here, here we have the derivative, and we see, the derivative is just the residual. And the negative gradient is just the negative residual. So it's not y minus h, but h minus y. And here we have to note that h of x is just the model output. This is just the prediction, it's a scalar. So it does not play a role in the derivative. We only have to find the derivative of the power, right, of the square. And you know how to do that, and then this makes sense. The derivative is equal to the residual. So making a step in the direction of fitting a model to the negative gradient is equivalent to fitting a model to the residual. And we convinced ourselves that this makes sense. And for any type of problem, we can apply this principle. We fit our models to the negative gradient, starting from an initial guess, maybe forecasting the mean. We find the error, we find the loss, and then continue adding models which we fit to the negative gradient. To that end, we need to be able to calculate that gradient, and again, this is then the contribution of the Friedman paper. It was nicely spelled out how we can do this for different type of modeling problems: regression, classification, ranking, survival, etc. So we can gradient boost regression models, classification models, but also survival models. If you happen to be interested in survival analysis, I recommend you trying that out. It's a nice non-standard way to build survival models. I also invite you to explore this visual demo where you can play around with different parameters of gradient boosting and see how the algorithm fits complicated functions. So you can visually convince yourself that it is able to fit complex, highly nonlinear functions. It's a beautiful demo, like it a lot. There are a bunch of packages which provide this algorithm, and these packages are important. GBM is the original Stanford package, co-authored by Friedman, probably programmed by one of his PhDs, I would imagine. And there are newer versions of the algorithm, XGB, or extreme gradient boosting in particular, but also light GBM and a few others. Gradient boosting is the boosting algorithm. It's the technique you want to work with, you want to consider when facing modeling problems. Personally, I use it always together with random forest. Random forest is easier to handle. Often it's slightly inferior to gradient boosting. And when facing a real world problem, I want to understand what does slightly mean, so I compare the two, and if the difference between the two is not too big, I'd rather go with random forest, which is just easier to handle. But when it comes down to accuracy, and we try to pool all the papers that have been written and provided empirical results of random forest versus gradient boosting, probably gradient boosting has an edge. So the same story as in AdaBoost. Typically, we use gradient in conjunction with shallow decision trees. So a decision tree which is shallow is simple and thus probably weak. As a matter of fact, I believe that in predictive modeling, it's really important to be aware of this. We use optimization always. Every model that we build uses optimization underneath to find parameters. Every model. Normally, when we use optimization, we care a lot about this local versus global, and we always want to find the global optimum, and if we don't, local solutions are no good. In machine learning, we want to produce predictions for new data that we not have, or we don't yet have available. I believe it's not so important to hunt for a global optimum, not to mention that it's typically impossible, because this global optima would be the global optima for the training data only. There is no guarantee whatsoever it would also be the global optima for the new data that is yet to come in, and most likely it wouldn't. So I don't believe that it's particularly important to, or you don't have to worry about that. And from a practical perspective, there is no need to try out any type of base model other than a shallow tree or a tree in boosting methods. Most packages would not even allow you to do so. Like these packages, they would not allow you to set the base learner to something else than a tree. But empirically and theoretically, there is little need to consider anything else. Trees are fast, so they work well. We started from the least square loss function and pointed out that regressing on the residual is a good way to improve our model, to reduce the error. And then we said, well, you know what? What we are doing here is actually we are regressing on the negative gradient, assuming a square error loss function. What if we face a problem where we don't care about square error loss, but about something else, like likelihood or cross-entropy loss? It turns out we can still use this principle of regressing on the error, just that we should not put in the residual, but the negative of the gradient. This is gradient boosting. And this is why we need gradient descent. We first calculate the gradient, and then we make a step in this direction. In an indirect way, though, this is a good point, in an indirect way, by building a base model. I wanted to quickly comment on these state-of-the-art packages. Gradient boosting came out in 2001. In 2002, Friedman wrote another paper, Stochastic Gradient Boosting, where he basically borrowed some concepts from random forest, specifically the concept of fitting a weak learner. When you do this regressing on the negative gradient, you don't take all the data. Instead, you take a bagging sample of the data. that injects some randomness and improves the generalization performance. So in stochastic gradient boosting, Friedman introduced bagging, and he also introduced this random subspace thing of random forest, where you just select a bunch of variables to consider for one of the Bayes learners, for one tree. And that was 2002, and then it took 14 more years until a paper by Chen and Gustrin came out in 2016, which introduced XGBoost, extreme gradient boosting. And soon afterwards, a few other papers came out, or packages came out. The focus here, the very, very core of that, is speed. Boosting is slow because you build the models incrementally. You need your ensemble to find the gradient of the error, and then you can build the next model. So you must do that sequentially. In bagging, you can just use 1,000 computers to build 1,000 trees in parallel, and then you put them together. It's much easier to scale a bagging algorithm than a boosting algorithm, because boosting is naturally incremental. So many years of school have thought about ways to accelerate boosting algorithms, and XGBoost is still one of the state-of-the-art approaches to carry out gradient boosting in the fastest way possible, let's say. One other feature often overlooked is that Chen and Gustrin introduced regularization, complexity penalties, which Friedman did not consider in his original paper, but the main focus really was speed. And GBM Lite by Microsoft also tries to speed things up. CutBoost is another package by Yandex, which is also one of these state-of-the-art packages. My opinion here is that differences between these packages are rather minor, and if you adapt with one of them, you'll be fine. You want to know one of them. In fact, they are very similar. Typically, I would not bother with comparing all three of them. My model of choice would be XGB. In certain applications, Light GBM will do better, in others it won't. Yandex CutBoost is claimed to be particularly well suitable if your data includes many nominal attributes with many levels. This is why it's called CutBoost. Categorical boosting, it's somewhat geared toward categorical variables, which happen to occur quite often at Yandex when working with search engine, right? Just in case. So when working with query data, you have textual data, you have many words. This is where categories come into play. Anyway, if you familiarize yourself with XGBoost, you'll be fine, no doubt. A few months ago, really, October I think, the Stanford Machine Learning Group published NGBoost. That is a technique to watch out for. It's not only a bit more, a bit faster or a bit less faster, or a bit more accurate or a bit less accurate than the others. That's a very interesting but complicated. So have a look at the paper if interested. I warn you, it's not an easy ride. They basically try to build a boosting model that incorporates functionality from Bayesian statistics, that you not only get a prediction, that's the key thing. You not only get a prediction for a data point, but you get an estimate of the uncertainty around that prediction. In other words, your model tells you, I predict that customer to be a good credit risk, and I'm 75% certain that she actually is. And another customer I classify also as a good credit risk, and there I'm 95% certain that she's good. So you get the whole density of you really get the density of the forecast. That's something that was, well, up until NGBoost, I believe, restricted to Bayesian statistics, and it was always the key advantage of Bayesian statistics to have this quantification of the uncertainty around forecasts, which can inform decision making very much. And this was the first paper that read this function into a boosting algorithm. So very worthwhile to watch out, but the code which is available is rather prototype-like. It's also fairly slow, so definitely not production ready, but I mean, many of you are in your first master semester. Eventually you will write your master dissertation. Something on NGBoost could be interesting. You don't really fit trees, you rather fit densities, and then you boost the densities that you fit. So you naturally work with densities. That's sort of the approach in a nutshell. I invite you to have a look into the paper to get the gist of it. There is also a blog on towardsdatascience.com, but this blog is only showing you the code and how you can get out these uncertainty estimates. By now, there is only this the original paper that explains the methodology. I'll skip over that in the interest of time. How XGBoost and LightGBM and others organize the acceleration, how they do parallelization, which is the key to speeding up algorithms, make use of CPUs with multiple cores, or even better, make use of GPUs. State-of-the-art boosting techniques can use that. They grow the individual tree in a parallel manner using the CPU or using a graphical processing unit, a GPU if available. This is how they basically speed up tree growing. I'll skip over these tricks, how they do that. Have a look if interested. For us who want to use these techniques, it's not dramatically important how they speed things up. You want to use one of these state-of-the-art packages because they are a lot faster than, for example, the GBM package, the original one, which is important if you work with larger data sets. For our class, if you only care for now about your assignment, the GBM package is fine. It's still fast enough to handle our data set. We don't give you that big data. In practice, however, you want to use one of these state-of-the-art packages. And the reason why they are not so easily applicable than, for example, random forest, is that there are many meta parameters to check, to consider. I put some here. The learning rate, how big is your strap in this gradient descent approach? You have parameters governing regularization in XGBoost shrinkage. How large is the bootstrap sample that you draw when you build a base model? How many attributes do you draw at random for a tree? And many more. We'll do gradient boosting in the tutorial, and we'll spend a lot of time on that, and you'll get some coding examples, how to do the tuning. It's just that this tuning is somewhat cumbersome. In random forest, you have two parameters. For one, there is a sensible default, and for the other, the larger the better. So it's very easy to use a random forest off the shelf, and you will still get quite good results. Gradient boosting needs a bit of more tuning, and this is why it's maybe less convenient. I have maybe 10 minutes left. That is the family of ensemble models. You want to know about vegging as foundation, random forest, and gradient boosting. And when I say you want to know about these are the things that you want to use in your work when you apply these techniques. Random forest, gradient boosting, important. Hence, we'll spend time in the tutorial on teaching you these techniques. They are also the most important ensemble learners out there. They are, however, homogeneous in that it's always the same base or weak learner underneath. Typically, it's a tree. Especially for bagging, you are free to choose other base learners. And you've seen this tiny bit of R code, which allows you to just implement bagging yourself. It's really easy. You can use any learner as base learner, any algorithm. Normally, it's only tree-based. And in this regard, it's homogeneous. And this also tells you what heterogeneous ensemble models are about. They combine multiple classifiers. So if you want to combine random forest and gradient boosting and logistic regression and neural networks and naive Bayes and whatever, you could do that by constructing a heterogeneous ensemble. These ensembles have shown very competitive results in papers and competitions like Kaggle competitions. As I said earlier on, from a practical perspective, the additional effort that needs to be invested is often not worth it. Okay, well, some ensemble learning taxonomy more. If you want to categorize different ensemble strategies, I put 3 dimensions here. How do you combine predictions? How do you construct the Bayes learners? And do you prune your ensemble or not? These are just 3 dimensions along which you can organize different ensemble algorithms, and they are still being invented in the literature. So developing new ways to construct ensembles. Typically, heterogeneous ensemble is still something that you would see in many papers that come out. It's more of a research exercise really than contributing to practice, I believe. An interesting dimension, maybe just briefly sketch it, the prediction strategy, static or dynamic. If you think about boosting or bagging or random forest as we introduced that, our ensemble forecast was the average over the Bayes model forecast. And for each data point, each customer that we score, we would do that. We calculate the forecast of all our Bayes models and average over them. That is static in the sense that we always use the same rule. There is a family of ensemble models that argue, why don't you try to construct the best average for each individual data point? Maybe certain models in my pool, maybe some Bayes learners, the first 100 models in my random forest, which could include 500 models. Maybe the first 100 are particularly well suited to handle data in a certain sub-area of my attribute space. Why don't I give these a higher weight whenever I observe data points that belong to that sub-area, ? That is dynamic ensemble selection. It's interesting, both empirically and theoretically. Just note that if you happen to be interested, that is something that you could explore in your research when the time comes, how this works, and there is still much work to be done in order to make a dynamic selection of ensemble members for an individual data point really work well. Let's come back to this dimension, heterogeneous versus homogeneous ensembles. Heterogeneous means we form different Bayes learners using different algorithms. In addition to considering different algorithms, we could also consider multiple metaparameter settings. This gives you a way to construct many models with one algorithm. Think about logistic regression. You have seen regularized logistic regression. You remember? There was regression with a penalty for complexity. And we had this parameter lambda in our loss function. You can run regularized logistic regression with lambda equal to 1. This gives you a model. And then you rerun it with lambda equal to 2, gives you a second model. And then you set lambda equal to 3, gives you a third model. So just putting in multiple values for algorithmic metaparameters, such as lambda in regularized logistic regression or the learning rate in gradient boosting, you can construct multiple models with the same algorithm. This way you can construct a large pool of models, and they are heterogeneous. And then you can construct an ensemble out of that. Don't want to go there. I want to show you one way to do that. stacking. The idea is you could split your overall modeling process into two stages: base model construction, base model combination. That's not much different from how boosting and other ensembles work. Just look at this table and then basically everything will become clear. If you imagine you have a data set and you fit 3 models to that data set using 3 different algorithms: random forest, logistic regression, gradient boosting. This is basically how your data structure will look like. You will have a test set, because you know how to organize your data, right? For this test set, you will know the actual outcome. I'm staying in my credit scoring picture. The label is good or bad, 0 or 1 for good or bad credit risks. And for each of my cases, my customers of the test set, I would have the forecasts for my base models. And it doesn't really matter whether they come from the same algorithm or multiple algorithms. This is how I can organize my data. It's just the same type of data we've been playing with for weeks now. It's a labeled data set. We have a label Y and we have columns. Okay, the columns are no longer the independent variables or the covariates or attributes. The columns are no longer x1, x2, x3, x4. They are predictions from certain base models. But still, we can think of these as independent variables, or they just look exactly as if they were. So in order to now aggregate these base model predictions, why not use regression? Or logistic regression if our target is binary for that matter. Why not run any type of second stage model apply any type of second stage model to this data? It will give you a sort of rule or a sort of weighted average over all your base model forecasts, so as to construct a pooled forecast, an ensemble forecast. And that's stacking. Very simple concept. Here's the recipe. Take some holdout data, build a bunch of classifiers on the training set, let them predict the holdout set, and then fit a second stage model onto this holdout set using the classifier forecast as independent variable. That is essentially the recipe. I think it's really intuitive. It's also very easy to do that. It's not easy to get it to work. It's surprisingly hard to really do it right. You have to think very hard about how you organize your data, how you cross-validate, etc. If you do it right, and there are some nice posts on Kaggle, how you should organize your data and when and how stacking works well, it's a bit more difficult in practice than I am showing it. But for the course, it's enough to know about the approach. You need to think, for example, about multicollinearity. Now you fit a regression model and the covariates are all independent forecasts. These forecasts will be heavily correlated. They all predict the same thing. So you will want to use a model that is robust toward multicollinearity. On the other hand, it's the second stage of your modeling. If you now need to tune your model a lot and you need to think about yet another way of cross-validation, things become really complicated. So you also want to use a model that is not too complicated to tune or does not have too many meta-parameters. What typically is used is either lasso or random forest. Things like that are fairly robust toward meta-parameters, work well off the shelf, and can cope with multicollinearity. If you are interested, I encourage you to check out this blog. It exemplifies how you should really put it into practice when you implement this algorithm. All right, time's up. So read through the summary. All these concepts should have come across, ideally, and then we are done with ensemble learning. Thanks for your attention, and I'll see you next week.